What's going on, guys? Thanks for tuning in today. We've got a fun little heat transfer problem for you. This guy right here, you can see the problem right here. It's problem 7.8 in the textbook. It's an external flows problem. So yeah, let's jump into this. A flat plate of width 1 meter is maintained at a uniform temperature of Ts is equal to 150 degrees Celsius by using independently controlled heat-generating rectangular modules of thickness A equals 10 millimeters and B equals 50 millimeters. Each module will be insulated from its neighbors, as well as on its backside. Atmospheric air at 25 degrees Celsius flows over the plate at a velocity of 30 meters per second. The thermophysical properties of the module are given as K is equal to 5.2 watts per meter K, Cp is equal to 320 joules per kilogram K, and rho is equal to 2,300 kilograms per meter cubed. So we have a diagram below. Part A asks us to find the required power generation, Q dot, in the units watts per meter cubed. We'll have to be careful of that later. In a module that is at a distance 700 millimeters from the leading edge. And then, again, we have our diagram. You can see our module is this guy right here. 700 millimeters in. We've got air at 25 degrees Celsius flowing at 30 meters per second over the outside of this plate. Then below is insulation, surface temperature, 150 degrees Celsius, and then, yeah, our dimensions. So, I cheated a little bit here, and I went to the tables to save us some time and found the properties of air at our T infinity. And then, yeah, noted that we want Q dot. So, I'd like to think about, I kind of like to think ahead to the end when problems like this, and then figure out what we're missing, because it kind of helps us to get a mental image of the path of equations we're going to use, and where to go. So, we know we want Q dot, right? So, what do we know about Q dot? Well, it's going to be equal to H bar times A times surface area times delta T. So we know delta T. Delta T is just T infinity minus T surface. So we know U, we know U, we need H bar, right? So what's the typical path we followed in past problems to get H bar? Reynolds number, because we have rho, mu, U, and a distance L. We get Reynolds number, we get it, depending on if that tells us it's laminar or turbulent, we use a Newton number equation, and then find H from there. So let's find our Reynolds number, given the info that we have. So REL is equal to rho U infinity times L over mu. So 1.1614 times 30 meters per second. And then for L, we're going to be measuring, because we're going to be interested in the average convective heat transfer coefficient, H. So instead of going up to the beginning of the module or the end of the module, we're going to want to go to the center, because that'll be the average distance from here to here, from the beginning of the plate to the module. So it will be 0.725 meters. And I'll show you the diagram again, just in case that was confusing. So 0.725, because L is 700 millimeters up to the leading, or the first edge, right? And then it's going to go in to the middle by another 25 millimeters. That gives us 725 millimeters for, yeah, a total of 0.725 meters. Okay? So all of that is going to be divided by our mu, which is 1.846 times 10 to the negative fifth. So let's look at what that gives us for REL. Plug this all in. Okay, we have 1.1614 times 30 times 0.725 divided by 1.846 times 10 to the negative fifth. That gives us 1.368 million. And that gave us a value of 1.368 million. And we know that for a flat plate, a Reynolds number greater than 500,000 implies that the flow is turbulent. Right? Okay, so it's very important not to jump the gun here, because your first inclination may be to go to the equation sheet, find a Newton number equation for a flat or external flow over a flat plate that is turbulent, and to to plug the Reynolds number right into there along with the Prandtl number. And then you get your H, and that's that. But you have to think about the Reynolds number that we've solved for here. We've solved for the Reynolds number across, or down the whole length up to the center of the module. And we cannot, by doing that and then just solving for H straight from there, would be to assume that the plate, that the flow rather, is turbulent the entire way. And that's not a good thing to assume. We have to check that. So how do we check that? Well, we know there's some critical distance x down the plate where the flow is going to be turning from laminar to mixed or turbulent. So we know that the critical Reynolds number, which is will be the Reynolds number at that distance x, is going to be equal to 500,000. And so we're going to take that 500,000 and we're going to set that equal to the Reynolds number equation, rho u infinity times x critical, that'll be the distance, over the same mu. So now we're going to take this, we have rho, we have u infinity, we have mu, and we have 500,000, so we can get our x crit just from there. It's equal to 500,000 times our mu, which is 1.846 times 10 to the negative 5. All of that is going to be divided by our density, 1.1614 kilograms per meter cubed, times 30 meters per second. And so that gives us an x critical value of, calculate, 500,000 times 1.846 times 10 to the negative 5 is 1.1614 times 30, okay? So, see that, 0.2649. That's a very good thing we checked that, because, let's refer back to our diagram. Our module is all the way down at 0.725 millimeters, or the center of our module is anyway. It's all the way down to 0.725 meters from the edge, right? The critical we just calculated is only 0.26, which is probably like somewhere around this region. That's a considerable distance in from, you know, where the module is, or from the leading edge rather, and there's even more distance to the module. So what that tells us is that we have a considerable distance of laminar flow that we need to account for. We can't assume that's turbulent the entire time, because that'll get us the wrong H. What that also tells us is that the total H to solve for Q dot is going to be a combination of the H for the laminar region plus the H for the turbulent region. So let's go ahead and get the laminar H first. So to get laminar H, we got to think about what Reynolds number we're going to be using. So the one we're going to use is the critical Reynolds number of 500,000. And the reason we do that is because it's laminar up until, you know, the critical distance that we just calculated. So we're going to use the Reynolds number up until that point, up until that distance x. So now, since we know that, also I should mention our PR from the table for this temperature of air is 0.707. So now we have everything we need to plug into the Newton number equation that we select. So we're going to look over to Newton number for flat plate laminar, and I've marked it over here. We're going to want to use this average Newton number across this distance x, and that'll get us our h bar, the average convective heat transfer coefficient, over this distance x. So that equation, NUX bar, is equal to 0.664 RE x to the 1/2, where REx is our RE critical, PR to the 1/3. And then we should also note that equals, Newton number is also equal to h bar laminar times our x crit over K. And then make another note, K from the table is 0.026 watts per meter K. Okay? That's a lot of Ks. So we know x crit, we know K, so we're just going to go ahead and plug everything in all at once and solve for h bar laminar directly. So h bar lam is equal to So we've got our Newton number equation here. We've got to multiply our k over and then divide by x crit. So 0.026 divided by 0.2649, that camera's still good, times 0.664. Oh shit, camera's not good. Times 0.664, REX, which is 500,000, comma, to the 1/2, times 0.707 to the 1/3. So if we plug that all into our calculator, that gets us an h-bar laminar value of, let's check, make sure I have the right, yeah, I do have the right table value, cool. So 41.05 watts per meter squared Kelvin. Okay, so now that's one part of our total h-bar down. So now we need h-bar turbulent. Not gonna use back of that. Markers bleed. So once again, now we want h-bar turbulent, right? So we're gonna follow basically the same process. We already have a Reynolds number that we're gonna want to use because it's up until the length to the module. That's what we're interested in. Yeah, so we'll use that Reynolds number. We already have PR because that's not going to change as temperature is the same for air the whole way across the plate. So this is a pretty straightforward calculation, even more so than before. So for this one, marked here, we're going to want to use NUL for, again, bar for average coefficient. That's what we're looking for. Again, flat plate, turbulent, external flow. And from here, it's just kind of a plug and chug, right? So we have NUL bar is equal to, and again, we'll make this early notation, turbulent. And now we're going to go, once again, to that L plus B over 2 distance, which we know is 0.725 meters, over K. And K also does not change. So yeah, 0.037 times our REL, which we determined before is 1.386 times 10 to the 6th. And this is all going to be to the power of 4/5. And then 0.707 to the power of 1/3. Right, so, and then, yeah, this K once again is 0.026. So we, once again, multiply this K over and then divide by this guy. And we end up with an H-bar turbulent of, let's see, let's calculate this bad boy real quick. We have 0.026 divided by 0.725 times 0.037 times 1.386 times 10 to the 6th to the power of 4/5 times 0.707 to the power of 1 divided by 3. Okay, so that gives us a H-bar turbulent as 96.8. 96.8 watts per meter squared Kelvin. And so now we have everything that we need to get our total H-bar. So our total H-bar is going to be, let's see, what was our value? 41.05, which is our H-bar laminar, plus our H-bar turbulent, 96.8, which means our total H-bar is equal to 96.8 plus 41.05, 137.9, we'll round. And once again, the units are watts per meter squared K. So once again, remember that we want Q dot, and we established earlier that Q dot is equal to H bar, which is this guy, we have him now, AS T infinity minus TS. Now, this is maybe exciting because you're near the end and you're about to get your answer, but remember from the beginning the units that we want. Q to be in. Q was requested to be in units of watts per meter cubed, which is a little different than what you're probably seeing for Q dot, but it's important to note it because it'll change your answer a bit. So what makes meters cubed? Well, that would be volume. So this will all be watts, right? Per meter cubed, we would divide this by volume. And then we can kind of take a little shortcut here to work with something a little more straightforward than volume. We have these two guys, right? What are the units of area? Well, meter squared. And then what are the units of volume? Meter cubed. If we cross off these exponents, what are we left with? 1 over meter. And then, so that's some distance. The distance that would be for us is our thickness A, which is 10 millimeters or 0.01 meters. So our Q dot equation becomes H bar over A times T infinity minus TS, right? So we'll plug in what we got. 137.9 divided by 0.01 meters. Remember, convert to meters to keep the units consistent. And then our T infinity, what was our T infinity? Well, actually, yeah, I converted to Kelvin because that's kind of a habit that I have, but don't be confused by that. It doesn't make a difference if you convert to Kelvin or leave in Celsius in this case because it's a temperature difference either way. So it's fine either way. But anyway, 423K minus 298K. Okay? Okay, that was a lot of K's. Anyway, this leaves us with our final answer for Q dot. And this is going to be equal to 137.9 divided by 0.01 times 423 minus 298. Just with a large number. 2, 3, 4. Yeah, so 1.724. 1.724 times 10 to the 6th watts per meter cubed. And that is our final answer.